Our project is over hydraulic jumps and weirs by Michael Cladney, Hollis Snell, and Jeremiah Medina.
A hydraulic jump, or a jump flow, is when a supercritical flow quickly and abruptly turns into a subcritical flow. When a supercritical flow meets a subcritical flow, water will seemingly jump or raise its water level abruptly while slowing down the water velocity, and it launches the water into the air. This is seen in nature with rapids and is also a man-made occurrence in order to prevent the erosion of structures. We will be demonstrating this ourselves with a small homemade model using water flowing from a gutter. Weirs are small dam-like structures built across rivers and streams that control water level and flow. The general equation for flow over a rectangular weir is Q flow is equal to the discharge coefficient times the length times the height of the crest over the weir raised to the 3/2. We calculated from our flow rate that the discharge coefficient for our weir was 0.699. The main issue with weirs is that most of them are static structures, so once they're built, there's no way to change the rating curve. This can cause issues because nature is highly variable, and during heavy rains can cause floods. This can be mitigated, however, through changing the geometry of the weir to increase the length.
The most important reason for inducing jump flow would be to go from a supercritical flow to a subcritical flow, typically to avoid erosion. To calculate the flow, we will need the Freud's number, which is given by the following equation of velocity divided by the square root of gravity over the depth of the water. To achieve velocity, we will need the Rn to the 2/3 multiplied by the slope to the 1/2 divided by the Manning resistant coefficient, which is dependent on the material. Now the Rn is equal to the area over the wetted perimeter. And we were able to find our first Rn is equal to 0.005643. And that our initial velocity would be 1.35 meters per second, giving us our first Freud number of 5.39, which is definitely a supercritical flow. Next, we will need the fact that the flow rate is equal to the area multiplied by the velocity. And we were able to determine that our flow rate was 0.000868 meters cubed per second. The flow rate remains constant throughout the process, and which is able to give us our second velocity, which is equal to 0.169 meters per second, which gave us our second Freud number of 0.2519. Knowing the second Freud number, we were able to determine that the flow goes into a subcritical flow because the Freud number is below 1. Continuing on with the mathematics, we see that the depth ratio is equal to 1/2 multiplied by -1 plus the square root of 1 plus 8 multiplied by the first Freud number squared, which gives us that our depth ratio is equal to 7.145. From this depth ratio, we are able to accurately determine the depth of the water after the jump, which will give us the height over the weir, which is needed to calculate the flow rate. This equation means that the flow rate is equal to the discharge coefficient multiplied by the length of the weir across the water multiplied by the height over the weir to the 3/2, which gave us our discharge coefficient of 0.699.
Nice.
In conclusion, we were able to successfully make a homemade weir and turn a supercritical flow into a subcritical flow using our weir. All of our calculations were also very close to the theoretical numbers we predicted. Thanks for watching our video, and we hope we helped you learn more about our weirs and jump flow.